is the isosceles triangle theorems. What is isosceles? What does that mean for us? Cameron?
Two or more angles that are congruent,
Careful.
that are similar,
Careful.
are the same size,
Careful.
are the same angle.
What did you use? What part did you say?
Triangle has two or more congruent sides.
Okay. A triangle has two or more congruent sides. Now what you said was a triangle has two angles that are congruent. Okay. Which we're going to find out that in every isosceles triangle, yes, that is correct. But definition-wise, an isosceles triangle is any triangle that has at least, keyword being at least, two congruent sides. Okay, what's at least mean?
Two sides that are
What's at least mean?
the least amount you can have.
The least amount you could have. So you could have,
1,500.
no,
Oh, wait. Two.
not for a triangle, right? So we're talking about sides, right? So if you have at least two, you could have
I saw
three, right? Okay. So in an isosceles triangle, definition is a triangle that has at least two sides congruent. Could have three sides congruent. But if it has three sides congruent, the way we do stuff in mathematics is probably better classify it, right? Because it does happen. What's a triangle that has three sides that's congruent? Cameron?
equilateral.
Equilateral. Okay, so the reason I ask this question is because everything that we learn about, let me phrase this real quick. So an equilateral triangle is isosceles, right? Would you agree with that?
Yeah.
Okay. And that happens 100% of the time because equilateral means all three sides are congruent, correct? Equal meaning equal, lateral meaning side, so all sides are the same. So if you got three sides that are the same, does that meet the definition of at least two sides being congruent?
Yes.
Yes. So an isosceles triangle, that condition is met every single time I give you an equilateral triangle. So the question is, everything we learned today about isosceles, is that always going to be true whenever you see an equilateral triangle? If I give you an equilateral triangle, I put it in your hands. Okay? You know it's equilateral, but you also know that it's isosceles, right? Okay? So everything that we learned today about isosceles triangles is true for equilateral. Is that okay with everybody? Okay. You hear the phrase, one you're probably most familiar with is a rectangle is a square, and a square is a rectangle, right? Okay. Those types of statements are prevalent throughout all of mathematics, okay? Not just geometry and dealing with shapes, but in the algebra that we do in mathematics, and a lot of definitions that we talk about in other branches of mathematics. It's very useful to know that an equilateral triangle, for instance, is already isosceles. Okay, so everything that I learned about isosceles triangles is going to fit for an equilateral. Does that make sense? Now, everything I learned about equilateral does not fit for isosceles. Does that make sense? It's an equilateral triangle. Every equilateral triangle is going to have three 60-degree angles in it. Can you imagine drawing an isosceles triangle where you don't have three 60-degree angles in it? Does that make sense to everybody? Let me draw an equilateral triangle here real quick. All right, so if I start with a segment like that, and I'm going to actually create an equilateral. It's called a construction. We're going to create it through the use of circles. Okay, so that circle has, you see that segment's the radius, right? Does that circle have the same radius?
Yes.
Okay, so when I do that, those two circles intersect a couple spots, right? I'm going to find those intersection points. All right, and what happens when I connect that segment and that segment? What is that triangle? It's equilateral. We can guarantee that by actually asking it for its distances, 4, 4, and 4, right? And I'm going to hide the hide the triangles here for a moment. Maybe.
How is figuring all this out?
Huh?
How long did it take you to figure all like, these buttons and stuff?
I'm still learning. But if we look at that, now the idea is that we should be able to determine also the angles of this thing. See what I mean? Still learning. So there's that angle 60 degrees, that angle 60 degrees, that angle 60 degrees, right? So that's equilateral, but it's also isosceles, correct? Okay. And no matter how I change those, always 60 degrees, but the sides are always equilateral, right? Okay. Now you can imagine, because the question I asked was, can you draw an isosceles triangle that doesn't have a 60-degree angle in it? Well, of course we can. We could take, that segment there. Let's see. I'm going to hide that line. Okay. Would you agree that that is isosceles? Okay. No matter how I move, G is going to maintain isosceles, right? Okay. But if I ask it for that angle right there, is it 60 degrees? No. Okay. I can make it 60 degrees. Maybe. I can get close to it, I guess. Close enough. So we can get there, okay? But we can also make triangles that are also not going to have that 60-degree angle. So this one here would be isosceles, but it's not equilateral, right? This one is equilateral, and it is also isosceles. So the things that we individually learn about an equilateral triangle, and we say that this is true for an equilateral triangle, would not be true for the triangle that we have drawn up there on the left. Does that make sense? But everything that we learned about that triangle on the left, because it's isosceles, everything that we learned about that triangle on the left is going to be true for the triangle on the right. Because the triangle on the right is bare minimum isosceles, right? But it's better classified as equilateral. A lot of things in mathematics, guys, you're going to find out that get classified that way. Kind of like a flowchart type thing, where we meet, on our way to being equilateral, we meet the conditions of being isosceles first. So once we get to equilateral, we have all the properties of the things that we kind of went through to get there. Okay, it's very, very important to understand throughout not just this course, but like I said, other courses in mathematics. A lot of textbooks do not kind of write that. They don't talk about that in geometry math, but say, hey, now that you know that this information is true for isosceles triangles, you also know it to be true for equilateral. They just make the assumption that you're able to kind of piece definitions together and understand how they interrelate with one another to determine that on your own. Okay. When dealing with isosceles triangles, now I'm going to focus on this terminology in an isosceles triangle that is not equilateral. Okay. So we have two sides that are congruent and a third side that is incongruent. They're not the same. Okay. Some terminology that we come up with is going to be used throughout the rest of the year. Okay, and it actually gets used in other types of figures as well, because we have things like isosceles trapezoids and terms like that. So other shapes can have the feature of being isosceles. And the same type of vocabulary comes into play when we talk about those things as well. So it's very important to kind of get a grasp of this now. But the two sides that are congruent, and anything that's isosceles is usually referred to as the legs. Okay. The angle that is created by those two sides in a triangle is referred to as the vertex angle. Okay, and that is the angle that often gets overlooked. People forget about that angle, but it's probably the most important of the three angles. Okay. And some of the things that we do in regards to relationships that get developed from isosceles triangles. And then The third side, the incongruent side, is referred to as the base. And then the angles that are created with the base in one of the red segments is referred to as a base angle. Okay. So we use that terminology. Here we say that terminology quite a bit. Now, we can do the same thing for equilateral. We can use the same terminology for equilateral, but the first thing we have to do, and I'm just going to go back to this picture here, the first thing we have to do is just kind of identify which angle we want to be the vertex angle, because they're all the same, right? And which angle then we want to be the base. Okay, so if I look at this and say, okay, I want this angle here, that angle there to be the vertex angle, okay, then that there would be a leg, that there would be a leg, counter. That is opposite the vertex, so that's the base. That angle there would be a base angle, and so would that one. That kind of make sense? But then if I want to make this one here the vertex angle, then the legs adjust and the base adjusts. Does that make sense? Okay. And then the base angle to adjust for, yes. Okay. So you can use the same terminology for equilateral triangles, but the idea is that you have to identify which of the 60-degree angles you're going to talk about as being your vertex. What is nice for a non-equilateral isosceles triangle, so the one on the left there, is that vertex angle, the one that has that green up there, G, that's going to be different. That's going to be different than angle E and angle F. So that's kind of the identifier for it being the vertex angle. Okay, and we'll talk about that as we move on, because if we look at the distances here, would you guys agree that 6 is different than the other two sides? Okay. So the other two sides are the ones that are congruent. They come together to make my vertex angle, and my vertex angle is then opposite my base. In this case, 6 would be the base. Okay, so it's very important to convince yourself of that terminology in those pictures, because again, it's going to be used over and over and over again. All right. The number one theorem that we're going to see in this chapter is section is the isosceles triangle theorem. The isosceles triangle theorem. Okay, it kind of sets the foundation for everything else that we learn in this section. Okay, it might not be it's the most important theorem, I think, for this section, but for this chapter and it's for this textbook, we're actually going to come up with a corollary here in the next couple slides that just gets used so much throughout the rest of the year, and it might be one of the most important theorems throughout the entire course. Okay? This is very important for being able to get to that point. And this says that if two sides of a triangle are congruent, so your if statement is setting up the condition that you have an isosceles triangle in front of you, right? If two sides of a triangle are congruent, then the angles opposite those sides are congruent. The angles opposite those sides are congruent. Okay? You guys remember a couple days ago, I think it was section 4.1 or 4.2, when we started first introducing the triangle congruency postulates. I gave you a triangle that had like differing side lengths, and I asked you, okay, if these are different side lengths, you should be able to look opposite those and find find the angles that are either smallest and angles that are largest. You guys remember doing that? Okay. Well, what this is saying is now I give you two side lengths that are the same. Two side lengths that are the same. Look opposite those. Okay. If the side lengths are the same, then the angles have to be the same too. Using that logic that we did when we try to order the three components, whether they be angles of a triangle or sides of a triangle based on the other components. So that should kind of be verification or a recognition that we know to kind of make sense to us. Okay. But what I want to do is I want to go through and prove this, because we've actually already proven this before, but I want to make sure that we recognize now the use and the benefit of everything we've learned so far in this chapter. Okay. So we're going to start with this. which this is the proof of the isosceles triangle theorem, which says if you have an isosceles triangle, and the if, remember, is your given. So, to talk about it specifically, for our picture, AB is congruent to AC. That's an isosceles triangle, right? That makes that picture isosceles. So we know we've met the if part. We then want to prove then the conclusion that opposite angles, angle B and angle C, are congruent. B is opposite AC, and C is opposite AB. Okay? Couple things here that we have to do in order to prove this. Okay, first thing, I'm going to just draw inside this triangle, so I want to make it a little bit more transparent. All right, so first thing, obviously, write your given down. AB congruent to AC. That's given. Step 2 is something that you probably don't know to do. Okay, but after you see this a couple times, you will know to do this. But we're going to construct segment A, let's call it AD, so that it bisects angle BAC. Look at angle BAC. That's the top angle, right? If it's an isosceles triangle, it's the vertex angle, correct? Okay. So BAC is an angle. Take any angle that you ever want to think about. You always cut it in half. Yes. Okay. And that's what a bisector does, right? So if every angle can be cut in half, every angle must have a bisector. Let's assume that we know where that bisector for angle BAC exists. We know it exists. I'm just going to draw it in. I want that segment right there to be AD. I know it exists, so let's just show it. Does that make sense? Okay. If you guys remember back to, we've seen this once before when I draw an extra line into my picture. We call that the definition of an auxiliary. I have trouble saying that word. Auxiliary line. I'm not going to say anymore. Because auxiliary means additional, right? Okay, and we know it exists. We know there's a point on B to C. Okay, so that segment BC, we know that's created by an infinite number of points. So we can highlight one of those and let it be D. And we know then that BAC is an angle, and that every angle has an angle bisector. So we just conveniently show that segment. All right? Does that make sense? And by showing that, we haven't violated anything. Okay? But it provides now two triangles, doesn't it? And what's nice about having two triangles, and the fact that one of these angles in the original triangle is now getting bisected. If this is an angle bisector, if AD is an angle bisector, what can you tell me about those two angles right there? What's an angle bisector do? Cuts an angle into two congruent parts, right? So one of those parts is BAD, angle BAD, and the other one is angle CAD. Definition of, I don't know why that red stuff won't disappear. Angle bisector. I don't know why that turned red. All right, so we now know that AD is congruent to AC. We've got angle BAD congruent to angle CAD. All right, and we might not be knowing kind of what we're trying to get to see these angles congruent, but maybe we're not sure what our next step is. So look at your picture. What have you created inside your picture? Two what? Two parts of the original triangle, right? So what is that's a triangle, right? You read that? And that's a part of the original triangle. And that triangle there, right? And if you have multiple triangles in your picture, what have we been doing for the last chapter? Trying to do what with them? make them congruent, right? Prove them congruent. So right now we've got two congruencies in the triangle on the left compared to the triangle on the right. What's the third congruency that we could use there? AD is congruent to AD, right? Reflexive property. Okay? So those two triangles now have three parts and both of them that are congruent, right? And what is the order that we see of those parts from the triangle on the left compared to the triangle on the right? AB is a side, BAD is a angle, and AD is a side. So we've got SAS. Okay, so we're going to say triangle BAD is then congruent to triangle CAD. By side angle side. So, if that's the case, what do you know about the first letter here compared to the first letter there? They're congruent. Angle B is congruent to angle C by what reason? CP, CTC. Now if I go back to my original picture, are those the angles that were opposite the two sides that were congruent? Yes. Okay? So my hope is doing this proof shows you the usage and the benefit of having the theorems and postulates that we've talked about so far. And ultimately having just theorems in general, because they end up leading you somewhere to new information. Now we know that if I have an isosceles triangle, by definition I have some congruent segments. But now we can also kind of piggyback off that and say, well, not only do I have congruent sides, I now know I have congruent angles. And it's always going to have congruent angles. Does that make sense? Okay. Here's another question. Now, don't write this down. Just kind of follow along with me. We knew that was an angle bisector, right? Okay. So it provided these two triangles to be congruent. What does that tell you? If those two triangles on the left and right were congruent, okay, this was D. Wasn't BD, first letter, last letter here? Shouldn't that be the same thing as CD? Well, if I draw that in my picture, BD and CD are those components right there, correct? So what's that called? What would D end up being for segment BC or for my base of my isosceles triangle? It's a midpoint. Good. Okay. So what we learn here is that in an isosceles triangle, if I bisect the vertex angle, remember A is the vertex angle. If you bisect the vertex angle, it's going to intersect the base at the midpoint of the base, always. Does that make sense? Okay. Here's another question. What do you know that maybe this blue angle here and that green angle right there, what do you know them to be to one another? What's the relationship between them? They're supplementary. Okay, they're a linear pair, right? And if I go through the names, BDA, BDA, B to D, and then back to A, and then C to D to A. And that maps out both those, that blue and that green angle, right? So it tells me they're corresponding parts, so it tells me they're the same. So Elijah says they're supplementary, and we also know they're the same, so they both have to be what? They add up to 180, and they have to be congruent. They both have to be 90. So they're both right angles, correct? So, what's nice is that when you have an isosceles triangle, okay? When you have an isosceles triangle, and you bisect, when you bisect a vertex angle, so let me bisect that vertex angle up here in this triangle, okay? I bisected that. The thing then that happens, always, a couple things that happen, is that the angle down there, let's see here, this angle down here is always a right angle, and you see that happen there, okay? And we also have then the idea that this distance from E to that point there should pop up a 3. Actually, I think I got to use points. E to there is 3. So E to H is 3, and H to F is 3 as well, right? So it shows you that when we bisect a vertex angle, it finds the midpoint of the base, and it's also perpendicular to the base. And that introduces, we're going to wrap all that up into one phrase. We got to know some vocabulary to be able to do this. Okay? And it's this last bullet. It says the bisector of the vertex angle of an isosceles triangle is always perpendicular to the base at its midpoint. That's what we just kind of walked ourselves through. Most textbooks are going to write it in red. It's going to say the bisector of the vertex angle is the perpendicular bisector of the base. Perpendicular taking care of the idea of right angles, and bisector taking care of that midpoint. Does that make sense? Cutting that base in half. Okay? So whenever you see perpendicular bisector, there's two components to that. You've got right angles, and you've got congruent segments being developed. All right? Is that doable? Now, what's kind of neat is in any triangle, when you do this, when you find the vertex angle, okay, and you bisect it, you will always then get congruent segments at the base and right angles at the base. But also, if you just start off knowing that you have an isosceles triangle and you get right angles at the base, okay, then you know that that segment also bisected the vertex and it also bisected the base. Okay, so you can start off with, and I've got an athlete here. Just because of time, we're kind of running out of time right now to kind of discuss this in full detail. But if you go to 4 or 5, we might be able to talk about it. We'll talk about it. These isosceles triangle properties here. Now this, just because we're zoomed out real far, it's kind of hard maybe to read some of this stuff, at least in the picture if you're far away. But what this is saying, we've got some preset conditions. Okay, right here my preset condition is that they're saying alpha is equal to beta. Well, alpha is just this angle right here where my cursor is, and beta is this angle right there. So basically we're saying when you have an angle bisector of your vertex angle, does that make sense? Alpha and beta are the same. Look at the conditions that apply. No matter what my triangle is, as long as I maintain that conclusion, maintain that condition that alpha and beta are congruent, no matter what my triangle is this angle ever going to deviate away from 90? No. So it's always perpendicular. Is the relationship between these two always the same? 3.94 is equal to 3.94, right? Now if I make the triangle bigger, now we get 7.74 equals 7.74, but the relationship is maintained, right? They're congruent. So when you start with an angle bisector of the vertex angle, you always get perpendicular and basically a midpoint here. Now this one here says the preset condition is now that we're going to look at a triangle in which I know that this segment here is congruent to that segment there. Okay, it's still isosceles, but when I have that, look at the conclusions I make. Is this still a right angle? So based off these two distances being equal, I now know I will still always have a right angle here. Are these two angles still the same? Yeah. So when these two distances are the same, the conclusion is that I get this right angle and these two angles to be congruent. Okay, so basically what happens, if I know that that's a midpoint, then I know that this here is perpendicular and it's an angle bisector of the vertex. Okay, and you can start to, I can manipulate this so those angles change, but you still get the relationship that those two angles are both 62.77 in this case. Okay. Over here, this one says, now you're going to start with the knowledge of just this segment being perpendicular to the base. So we're starting off with the right angle right here. That's all we know. But if that's what we know, look at the relationships that happen. What do you notice about these two distances? They're the same, right? What do you notice about these two angles up here? Are they the same? Okay. So there's 3 pieces of information here. And what we're learning here, what we're coming up with these properties, is that if we recognize one of those conditions to exist, the other two have to exist as well. Okay. This is the converse of the isosceles triangle theorem, which is just taking the if and then and flipping them. So now you're going to start off with 2 angles that are congruent, and then go opposite those 2 angles, and now you know you have 2 sides congruent. Okay. So this is starting off not knowing that you have an isosceles triangle, but knowing that you have a triangle with two sides congruent, and when you have two angles congruent, and when you have two angles congruent, you can make the argument that two sides have to be congruent, and then when you have two sides congruent, that classifies the triangle as isosceles. Okay? You're going to see some homework questions, and we're going to kind of skip over kind of the boring ones here. Some of them just ask you, can you look at this and determine whether it's isosceles or not, or whether certain things are congruent or not. So for instance, maybe this one they ask, is GK congruent to HK? Is GK congruent to HK? So highlight GK, highlight HK, visualize those things. Okay, so I'm going to put markings in them for you. So we're going to look at that segment compared to that segment. Okay, are they congruent? Do we have enough information to say they are?
Yes.
Yes, why?
Because the two angles are the two angles are the base angles, and the base they have the vertex up top.
Good. So you're saying that this here and this here are base angles, right?
Yeah.
And because those are congruent, then the sides opposite those are also congruent, right? That's the converse of the isosceles triangle theorem. What is all this other junk here? It's just clutter to confuse you, right? Okay. They go on to ask, is HL congruent to KJ? HL is just that distance right there. KJ is just that distance right there. And if you look at those are not full components of a triangle, right? Okay. And there's really no work that we can do here. I'm just going to answer this for you right now. There's really no work that we can do there to show HL and KJ to be congruent. Okay. They'll give you a question like this: Is AB congruent to CB? Is AB congruent to CB?
Yes.
So is that segment there congruent to that one? Why?
Because the two base angles.
Yeah, because angle A and angle C are congruent, right? What's DE in there for?
Clutter.
Clutter. All right. Eliminate the things that you don't need. Is that doable? You see a handful of questions like that, but the ones that are a little bit more useful are things like this. These are the kind of questions that we're going to focus on. What relation can you set up to kind of work through this problem? All right, so we use, just like what we've been doing throughout the entire year, we learn a theorem that provides a relationship, and then we start applying that inside pictures, right? Okay, with algebra. I'll let you guys solve that on your own. This one's a little bit more difficult, so we'll do this one together. We look at this figure in, how many isosceles triangles do you have up?
Two.
You have two, right? Okay. Now, they asked me to find the measure of angle 2 out here. Okay, or I guess I'm trying to find maybe my directions aren't really great here. Maybe we're just trying to find x. Maybe we actually want to know the definitive value for angle 2. But that's not an angle for our triangle, right? If you guys remember, that's referred to as an exterior angle, right? Okay. But it's attached to an isosceles triangle that I really know nothing about. Okay. But if I look at just one of these isosceles triangles, let's just look at that blue one. Okay. Whether this is information that you're going to need, I don't know. You can probably get to the answer a little bit quicker than doing what we're going to do here with that blue one. But do you know two parts or two components of that blue triangle? Yeah. You know the two angles at the bottom, don't you? You know, because this is isosceles, that angle right there and that angle right there, the angles that are opposite the congruent sides have to be congruent too. So what's 180 minus 34?
56.
Huh?
46.
146, right?
146.
So if I got 146 degrees for those two angles, what's one of them got to be?
43. 100. No. 73.
73. They're both got to be the same, right? Okay. Now, does that help me?
Yes.
Not in getting into that other triangle. What really helps me in getting in that other triangle is knowing that angle right there. And that angle, along with the 34, should add up to what? Careful.
90.
90, right? They put that little box there, right? So tell me if these two angles here are complementary. So this one's got to be 56.
Question.
Yeah.
If we're trying to figure out what 180 is, then why don't we just subtract 180 from 136? If we're talking about what x is, 138. We're trying to find what x is. Can we just subtract 180 from 138?
Huh.
Why?
Because this is x plus 138.
Yeah.
We're trying to find what x is. We don't know if that's x. Because that's what you're saying when you do that.
Yeah.
We don't know if that is x. We actually now know that's what?
56.
56, right? And maybe doing a little bit of legwork here. If that's 56, that's 112, right?
Yeah.
What would this angle here be? 60. Okay. So whether I need that 68 or not, we now know we have enough theorems and definitions to kind of go through and find a lot of information about that triangle, right? Okay. What is also nice to know, I don't need this, but this distance I know is not the same as that distance and that distance because that angle right there is different, right? Okay. So that's some nice information to know. But now what you were saying earlier is, now I have the two things there to add up to 180, right?
Yeah.
The logic that you were trying to use, and some people do, because we didn't know that 56 initially, so you said, let's just let that be my variable, right?
Yeah.
Let that be my unknown. Well, you can't let it be a variable that you're already using. So if you're going to do that, you would have had to let it be y. So then you would say y plus x plus 138 equals 180. But now we know that that y value is a specific 56. So say 56 plus x plus 138 is equal to 180. What's 56 plus 138? What's 50 plus 130?
94.
What's 50 plus 130? 180, right? What's 6 plus 8? 14. What's 180 plus 14? 194. Okay, so x plus 194 equals 180, so x is negative 14. Can x be negative 14?
Yeah.
Yes. X can be anything it wants to be, right? Anything the algebra tells us that it is, it's fine. But what is the problem? If x is negative, when I plug it back in, I got to make sure what? You got to make sure that that angle there is always a positive angle, right? Okay. When I plug negative 14 in, what do you get? 124. Okay. Now, there's a built-in check. Okay. And what I like, somebody in the last class said, yeah, if you want to check to see if you did this right, plug negative 14 in here, and see if you get 180 on the left-hand side. Perfectly fine. That tells me that every step I did after I wrote that equation, my algebra was right, correct? But I want to check, that's going to tell me that the equation I set up was also right. Does that make sense? Okay? And just plugging in doesn't do that. But doing this does. 124, that's an exterior angle, right? And 68 and 56 are those remote interior angles. You guys remember the relationship between an exterior angle and two remote interior angles? The exterior angle should equal the sum of the two remote, right? So 68 plus 56 give me 124. Okay? So that check is nice because it not only validates the negative 14, but it validates the 56 plus x plus 138 equals 180 was an appropriate, was an accurate equation. All right? I want to do one more real quick with you because you're going to see something like this, whether in your homework or test or quizzes. It says triangle ABC is isosceles with vertex angle C. If measure of angle A equals x plus 6 and measure of angle B equals x squared, find the measure of angle C. Okay? They ask you to find angle C. Is there an expression up there for C? No. Okay? That's where people struggle with this stuff. When they give me triangle ABC, the best thing to do here is to organize your information in a picture. Okay? Does not matter what your picture looks like. You put A, B, and C anywhere you want to, but I'm going to draw mine that way. C is the vertex angle, right? So when they say that, they're hiding a congruency to me. Because we have to know what our definition said. Okay? And the vertex angle C was the angle that was created by two congruent sides, right? In that picture that I showed you at the beginning. So it tells you that AC is congruent to CB. All right, by telling me I have an isosceles with vertex at angle C. Now, if I know that, what's that tell you about B compared to A? They're congruent. That's the isosceles triangle theorem, correct? So now do you have expressions for A and B? I'm going to x squared is equal to x plus 6. Now, when I see x squared, what's the first thing you want to think about when you see something x squared, algebraically? What's the process? Anybody remember? Starts with an F, factor. Okay, so that's the first thing that should come to mind. When you see the word factor come to mind, the number 0 should come to mind. You want to get everything equal to 0, so you got to move one side to the other side. Okay? And that kind of gets the ball rolling in what we need to do. You guys remember factoring, at least right now, your techniques that you're probably most familiar with, looking for a number to multiply, you got to give me -6, and have to give me -1, right? What are those two numbers? -3 and +2. So now, because those two things multiply together to give me 0, I go x minus 3 is equal to 0, and x plus 2 is equal to 0. So now I get two solutions, x is 3 and -2. If you remember last week our discussion, we could write our answers this way, as a set. But what we want to do, we want to find angle C, right? X is not angle C. X isn't even angle A or angle B. I need to plug these answers back in and see if I get true information. And then if I get true information, where does that lead me for C? So this was x squared, and this was x plus 6, right? Plug 3 in. What do you get when you plug 3 in right there? 9. What do you get right there? 9. Are those okay angle measurements? Yes. So if that's 9 and that's 9, that's 18 total, right? So if x is 3, measure of angle C is 180 minus 18, be 162, right? Okay. What if x is -2? What's -2 squared? 4. What's -2 plus 6? 4. So you've used 8 degrees, right? So what do you got left over for C? 72. So with that information, with that criteria at the onset, there are actually two different triangles that can be made from that. Does that make sense? Sometimes there'll be 2, sometimes there'll be 1. Every once in a while there might be none. Okay? We just have to go through and check things to make sure we don't violate any other properties, so we can classify our solutions. All right? There's an assignment in Math Excel. We'll continue to talk about this stuff in the next couple days. I will right now.